Welcome to another video. So for this one we have November 2016. I'm not sure what province it is because it was not specified on that cover page. So now this is another classical example of a Newton's second law problem. So in this case we have a tow truck, and this tow truck is pulling that car. All right, and then we are given the force applied by the engine of the tow truck, which is 9,000 newtons, and then the mass of the tow truck is also given as 1,300 kilograms, and then the car 950 kilograms. So these two vehicles are then connected to each other by an inelastic tow bar of negligible mass. Well, in South Africa, the law says you must use a tow bar. It's unfortunate that people use ropes instead. Anyways, so we have this, and then we are told that this tow bar, so these two vehicles, the truck and the car, are moving at a constant velocity. Immediately, you must come here and tell yourself, actually, tell your mind that as soon as they mention constant velocity, it means acceleration is not there, or it means our acceleration is 0 meters per square second. Okay, so some people don't know the difference between this. Okay, this looks weird. A is 0. There are some people that don't know between this and this. One is meters per second, the other is meters per second squared. Right, this one is for velocity, while this one is for acceleration. Always remember that. So that's one thing you must know. Okay, so now remember what we always do. We annotate. In this case, our diagram is a bit hard to annotate, but let's try. We have this car. In this car, we will have a normal force. This looks messy. Or let's just throw the free body diagrams of these two things. Say we have the tow truck and the car. Right, so I've divided it into two. Then I have the tow truck and the car. Okay, so this is just for me to know everything beforehand before I start answering any questions. I'm confident that I know all the forces and every other piece of information that has been given to me. So yeah, let's start with the tow truck. Our tow truck has a normal force. Okay. And what else does it have? It has the force being applied by the engine, which is to the left. It is 9,000 newtons. Then we have the the weight of the tow truck. And then they said it's being pulled on a gravel road, so we have to assume that there's also friction there. Maybe FK, because these two are moving. And then now we come to the car. The car will also have normal force. Normal force is perpendicular to the surface, and then it has the mass. Why do I keep saying mass? The weight. And then it has tension, going that way from the toe bar. Oh, I forgot tension on this one. From the toe bar, tension going that way. And then there's friction here. Okay, so we have these forces that are acting on the tow truck and the car respectively. So now we have everything we need to know about the situation, I think. So let's start with our answering. Question 1, define the term frictional. So in this case, we are just asked to define frictional force. The question was not specific whether or not we are defining static or kinetic friction. So the distinguishing factors or the distinguishing keywords that we usually see in those two definitions, we must not include them in this specific definition. So what that means is, if you remember, static friction, we say it's the force that opposes the motion of, or that opposes actually not the motion, it opposes the tendency of motion of a stationary object, while the kinetic friction is the force that opposes the motion of a moving object relative to the surface. So relative to the surface is common in both definitions, but one is for moving objects, the other is for objects that are stationary. So we won't include the keywords like stationary and moving. So now what we can say is it's the force that opposes the motion of an object and which acts parallel to the surface. Just a general definition of what friction is. So if you remember, friction can be on the surface or on air. And then this is the definition we would use. Well, this one limits the friction to objects that are on a surface. So we don't include objects that are moving in air and so on, which makes sense because you will barely see object where you have to account for air friction, right, or air resistance. So this is the definition that you would have, and then I believe this is also on your exam guidelines. So you don't use just any definition, you use the ones that are provided to you on the exam guidelines. Okay, so now we go to 4.2. We are asked to name and state the law that explains why the force exerted by the tow truck on the car is the same as the force exerted by the car on the tow truck. So first of all, let's name what's the law that says the force exerted on the tow truck is the same as the force exerted by the car on the tow truck. So that's Newton's, let's do this, third law. You write it there, Newton's third law. So you write Newton's third law of motion and then you state it. So in a nutshell, what Newton's third law of motion says is if object A is applying a force on object B, right, object B will apply a force of equal magnitude to that applied by object A, but in the opposite direction. So a good example of this is if you imagine yourself pushing against a wall. Say this is your wall, right? Say this is your wall. Now you come here and you apply a force on this wall using your hands. This is Fu on wall. This is a very long name for the force, but you should get the idea. U on the wall. What the wall does, it takes the very same amount of force that you are applying to it and then it applies it back to you, but in the opposite direction. That's what the law, Newton's third law of motion, says. says. So this is F wall on you. So that's what this law basically says, right? So then you can state it and say there are keywords that they normally look for in these definitions, so you have to stick to your exam guidelines. Usually teachers would give you a list of definitions from the exam guidelines. Just make sure you stick to those, even though you understand the definition, but don't write it with your understanding. Memorize it, because they want the keywords there. All right, so what it says is when object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. That's what the official definition of this law is, the one that you would likely find on your exam guidelines and so on. So that's basically what the law says. When object A exerts a force on object B simultaneously exerts a force, or an oppositely directed force of equal magnitude on object A. So what that means, if we were to put numbers to it, if you apply 50 newtons on this wall, 50 newtons of force, the wall will apply to you minus 50 newtons. That minus means it's in the opposite direction to what you are applying, and the 50 newtons is the equal magnitude, which is the same between the two forces. That minus just adds a bit of direction. Of course, that's assuming we choose left as positive in this particular example that I'm showing you here. So this is in essence what the law says. Okay, so that's what you would have written. Of course, you wouldn't include this diagram. This diagram was for me to illustrate to you. You would include this part and that part. I think there should be 3 marks. Let's check. Yeah, it's 3 marks. 1 mark for the law and 2 marks for the definition. So the keyword they look for, one of them is this: simultaneously exerts an oppositely of equal magnitude. So these keywords are important. I think it's simultaneous, opposites, but yeah, your definition has to have, to some extent, all of these keywords. Okay, so you must make sure that before an exam or a test you memorize your definitions, because you don't just write them based on what you think they are. Otherwise you won't get free marks. These are free marks. Definitions don't require a lot of work, unless, let's see, now let's go to 4.3. Draw a labeled free body diagram indicating all the forces acting on the tow truck. Okay, we've already drawn our free body diagrams, so I can confidently take this. And put it here. This is our 4.3. Okay, we're done with 4.3. And then we have 4.4. If the coefficient of kinetic friction between the tow truck tires and the road surface is 0.45, okay, calculate the, then we have 2 sub questions. So now we have to find the magnitude of the tension in the tow bar, given that mu k is 0.45. That's a very high coefficient, 0.45. okay, let's go find the tension. So if we check our diagram, we can either use the car's free body diagram or the tow truck's free body diagram to find the magnitude of tension. This one just has 2 forces, so I think we should use the car so that we can just finish fast. How many marks is this? 5. Okay, And then let's just make sure, let's read carefully to make sure the coefficient is not for, okay, coefficient of kinetic friction between the tow truck tires. Okay, it's for the tow truck, so you can't use the car. Let's use the tow truck free body diagram. All right, and then let's start. First of all, when we sum forces, we will have this unknown Fk, right? But the reason I'm focusing on this unknown is because we have just been given the coefficient, so it means we can find it and eliminate it before we even take sum of forces. While this guy will also be an unknown, but it's fine because we will find it during the operations of that equation, which is the main point of this calculation. So let's start by finding Fk instead. If you want, you can combine and find Fk during your calculations. For instance, you say Fnet is equals to MA, and then you substitute and find Fk during this calculation. You don't have to separate them. I just prefer separating them so that you see every value. So we will say Fk is basically mu k times n, right? This is 0.45 times n is, in this case, there's only normal force and the weight along the perpendicular direction or in the vertical axis. So what that means is we can simply say, we could have started with that actually. We can simply say n is equals to weight. N is equals to weight, which is equals to mg, right? So therefore we could have said here mg, and then now we can multiply with the tow truck is given to be 1,300 kilograms, and then we can find our answer. So that is 5,733 newtons. So we're done with Fk. Now let's take sum of forces in the horizontal direction, because that's where T is located, and we need to find T according to this question. So we say the net force across or along the horizontal axis or the x-axis is MA, and we are taking, I like taking the direction where the object is going. I like taking that direction as positive. It makes my life easy because I don't have to come and change the sign for A. I just leave it as it is. So I leave it as positive. So now we have 9,000, which is the force that the engine applies on the truck, minus, or let's say plus, we don't know T, plus, we know Fk, but let's just do this for now. I'm adding an extra step. It's unnecessary, but I want to check everything. So now you have minus T minus 5,733, and then you have 1,300. We were told that this thing moves at a constant velocity, so we can put 0 here. Acceleration is simply 0. So from here onwards, we'll say 9,000 minus 5,733. That gives us 3,267 minus T is equals to 0. Therefore, T is 3,267 newtons. Interesting. So now we are confident that yes, we have done the things. So this is what your 5 marks would have came from. And then what I was saying is what you could have done as well. You see this whole step, this one, you could have had it here. So that's still okay. There are people that prefer it like that. So what I mean by that is you could have said 9,000 minus T minus 0.45 times 1,300 times 9.8 is equals to 1,300 times 0. You see, you just calculated friction, but in the same step where you are going to be in the same calculation where you are going to do to find your tension. That's very much acceptable. Actually, there are people that prefer it like that because it minimizes space usage. So if you are into that, that's completely fine. You'll still get your full marks. Okay, so yeah, that's it. But what would happen is you'd have to show us this formula somewhere midway here. So maybe here after this step you would have had a step that says 9,000, because sometimes they mark the formula, so you never know, minus T minus mu K times mg, something like this. Then you come to this step. That's completely okay. So you are safe if you did it in 2 different steps, because you know that they will find everything that they're looking for here. You don't have to worry. So that's what we have, guys. And then now let's do the coefficient of kinetic friction between the car tires and the road surface. That's 4.4.2. So we are looking for mu k, but for the car, because the one that we were given in the problem was for the truck, the tow truck to be specific. So we know that if we come here and take sum of forces along the horizontal line, or along the horizontal axis, sorry, we'll have T and Fk. We already know T, so we can find Fk in that one equation alone. And then from there, we can just calculate mu k. Let me show you what that looks like. Sorry for the scrolling. If it's making you dizzy, there's no better way I can do it. I can move slower though. Let's see. Boom. Okay. So now we can say Fnet is equals to ma. You will use this equation until you are tired of it, in this chapter at least. And then I still choose that side as positive. I'm consistent. In here you could have chosen any direction really. Then you have T plus minus Fk, which is ma. Let's substitute. I have T minus mu k times, I almost said n, is equals to ma. Okay, here I'm combining, guys. So let me do it step by step. So T minus mu k, this looks tedious, mg, because n is just mg. So you could have said here, before you started this, you could have declared it here that n is equals to weight, which is equals to mg, right? So you could have said it there. And then now you come here, say it is equals to ma. Then you can substitute your values. You will have T being 3,267 minus mu k times 950, which is the mass of the car, times 9.8, the constant, is equals to 950 times 0. Here I have the liberty of just saying this whole thing is 0, but I don't know whether or not they will want to see that I substituted 0 here, so I just do it anyway. I substitute my 0, but I know that anything multiplied by 0 is 0. So from this step to this one, I could have just said all of this is 0, but to avoid losing marks, I write everything. Okay, so yes, let's continue. From here is just maths. You can take your mu k to the other side and then divide. So what's 950 times 9.8? That's 9,310. So you'll get mu k is equals to 3,267. Then you divide both sides by 9310, which is 9,310. And then your mu k will be 2310 0.35. That's your answer. Yes, my 5 looks like an S, but it's a 5. Yeah, proper. Let's move this thing up. Looks good. Much better. All right, so yes, this is what you would have done, guys. This is what you would have done. This is your work that you would have done. So now we go to the next part of this question. We are being told that suddenly the tow bar between the car and the tow truck disconnects and the car comes loose. Okay, that's an interesting scenario. And then, using a relevant law of motion, explain why the car continues moving forward for a short distance. So let's bring it back to the original scenario. Initially, before the tow truck, before the tow bar, before it disconnected, these two vehicles were moving at constant velocity. So we're being asked to use a relevant law of motion to explain why the car will continue moving at this constant velocity. Do you get where I'm going? So if you remember, there's our law of motion, the first law of motion, that says an object will continue in its state of rest or constant velocity or constant motion unless acted upon by an unbalanced force. So that's what happens in this scenario as well. No unbalanced force acted on this car, so it was still moving at a constant velocity when the tow truck disconnected. The tow bar disconnected. So it will continue moving unless someone tries and come to try and stop the car. That's an unbalanced force. The car will then stop, right? It will stop continuing at constant velocity. Okay, so that's what the law says. We see it, it's also called the law of inertia. So some call it the law of inertia, we call it the law of first, Newton's law of first. Okay, let me slow down. Newton's first law of motion. Some call it Newton's first law of inertia or Newton's law of inertia. Right, so it's the same reason that whenever you are in a car and then the car is moving at a certain speed, you have your seatbelt on. Let's say you don't have your seatbelt on actually, and then all of a sudden whoever is driving the car slams the brakes, right? All of a sudden, because maybe some guy is doing stupid things on the road and you have to brake fast before you hit them, right? So when that happens, you will see that your body will move forward in this quick motion. Boom! You might even kiss the dashboard there if you are not aware, right? So that is because of the law, the first law of motion. So your body wants to continue moving in that constant velocity that you were moving at, right? So that's why it keeps going forward, right? So that's basically why that's basically what this law says. This was an interesting question actually. It combined all the first three laws of motion from Newton. So yeah, this was a very, very interesting question. You had to know your stuff here, otherwise you would suffer. So let's answer this question. We are saying the car continues moving after the tow bar has disconnected due to its inertia, right? So in essence, we are saying that, so according to Newton's first law of motion, this is how we are now answering now. According to Newton's first law of motion, an object will continue in its state of rest or constant velocity unless acted upon by an unbalanced force, right? So therefore, after the tow bar disconnects, the car will continue moving forward due to its inertia. That's what we would say. right? Because that's the reason you almost kiss the dashboard whenever someone suddenly brakes a moving car. Okay, it's the inertia. Okay, so now that's what our answer would be. And then this, yes. So I've written it here for you to check out. Oh, my 5 looks funny. Good. So according to Newton's first law of motion, this guy, what's happening? Okay, I don't know. An object will continue in its state of rest or constant velocity unless acted upon by an unbalanced force. Hence, I think hence usually has a punctuation. I can't remember. Hence, when the tow bar disconnects, the car continues moving forward due to its inertia. Basically, everything I just said, I wrote it there so that you can see it too. So now we have 4.6 after this. What is 4.6 saying? Let's move slow so that you don't get dizzy. Calculate the acceleration of the car as it comes to a stop after a short distance. Ooh, this is interesting. So now the tow bar is disconnected. Let's come back to this. Once the tow bar disconnects, do you understand that this means that now we won't have tension being part of our free body diagram anymore? We will now have friction, kinetic friction. So that's the only force that we now have, unfortunately. So if we want to calculate the acceleration as the car, of the car as it comes to a stop, we will only have friction there. So it makes sense to still use our free body diagram, but now we will have to remove tension. Okay, we can't include tension anymore because the tow bar is disconnected, so there's no more tension. It was only there when these two cars were still connected. So we can still say Fnet is equals to MA, and I'm still choosing the direction of the car as positive. This means friction will still be negative, is equals to MA. We found friction to be 3,267, and the car's mass is 950 times A. To find A, we divide both sides by 950, and then A is minus 3.45. Don't be scared when you see this. I know in all the examples we've been doing so far, we've never seen a negative acceleration. So let me put you into perspective what it means. So this negative acceleration, in case you don't know, it means the car is slowing down, right? Remember, acceleration is also a vector. So the ones that we've been calculating before, they were positive because acceleration was in the direction of motion where we were going. So if the car was going to the left, acceleration was going also to the left. The car is accelerating to the left. But what happens if the car is accelerating to the right but it's moving to the left? So physically what that means, it just means it's slowing down. This is an example of how you would represent the acceleration of a car that is slowing down at a constant rate. Okay, so that's what it means physically, and it makes sense if you think about it. Friction is always trying to resist the motion of the object. So if it's the only force present in the system and the system is moving, the system cannot go on forever. It has to slow down. So that's why our acceleration is negative. You've also seen this. If you like to play around either with tires or whatever, or a toy car, if you push it hard and then you let go, it will go until it slows down and stops and comes to a complete halt or stop. The reason for that is because there's friction between the tires and the surface. So this friction is constantly being applied on the car and causing it to slow down until it stops completely. So that's another way to visualize it, or another way to think about it. Okay, so that's what friction does. Obviously, we won't see it while the force that is being applied is greater than the friction, because the friction will be overcome. So the car will just keep going, keep going. As soon as we remove the force, friction takes over. It slows down the car until the car comes to a stop. That is, ladies and gentlemen, how you would think about it. And then, with that being said, I think we are done with this cool question right here. So 26 marks. It makes sense. They combined all three laws in one question. Very sophisticated, I tell you. So now, not too sophisticated though. I'm just giving a compliment here. So now that's it, guys. Thank you. I'll catch you on another video.